Hi friends, are you ready to be a scientist like George Ohm and do an experiment to derive Ohm's law? We are going to use this setup to do a simple experiment for Ohm's law. We will learn the concept of resistance. The word resistance means to oppose. Just like during the holidays, you may have a resistance to get up early, or you may have a resistance to study. Similarly, do you know that in a wire there is an opposition, a resistance to the flow of current? I'm going to make these concepts really easy for you, and I hope after watching this video you won't have any resistance to try the quiz and the top 3 questions on this topic. Links are given below the video. Ohm's law is a very important law in electricity. Ohm's law gives us the relation between electric current and electric potential difference. Now, do you remember what is electric current? Electric current is the flow of electric charge, and numerically it is defined as the rate of flow of electric charge. The formula of current is charge divided by time. Now, what is the unit of current? That's right, the unit of current is ampere. Now let's talk about potential difference. The potential difference between 2 points in an electric circuit is defined as the amount of work done in moving a unit charge from one point to the other point. The formula of potential difference is work done divided by the charge. And what is the unit? Correct. The unit is volts. Electric potential difference is also known as voltage. Potential difference is like an electric pressure that is pushing the charges to move in a circuit. So potential difference causes electric current. Now we want to see how electric current changes when the potential difference is increased. Let's take a look at our setup here that we are going to use. This is our voltage supply. It's called a battery eliminator because you don't need to use cells like this. We can change the potential difference supplied by it by turning this knob. As you can see here, we can get different voltages like 2 volts, 4 volts, 6 volts and all the way up to 12 volts. This voltage supply supplies DC voltage, just like a simple cell. DC stands for direct current. Current flows only in one direction. The voltage supply is connected using this red wire to this instrument called an ammeter. The ammeter is used to measure electric current. And the ammeter is connected using this wire to this black box. The black box contains a nichrome wire in it through which current can pass through. This is usually called the resistor. We are going to measure the current passing through the wire in the black box and the potential difference across the wire. To measure the current through the wire, we will use this ammeter. The ammeter is connected in series with the wire in the black box. To measure the potential difference across the wire, we will use this instrument called the voltmeter. As you can see, it is connected in parallel to the wire. If you draw the circuit diagram for our setup, it will look something like this. Here is the nichrome wire that is inside the black box. The voltmeter, which is marked with the V symbol, is connected across the ends of the wire. The voltmeter is connected in parallel. And the ammeter, which is marked with the A symbol, is placed in series with the wire. Do you notice that the battery is marked with an arrow? Since our battery is a variable voltage supply, we can change the voltage of the battery. For our experiment, we are going to change the potential difference across the wire which is inside this black box by turning the knob on our voltage supply. And we'll make a table of our observations. the values of potential difference across the wire and the corresponding current in the wire. So are you ready? Let's go ahead and start our experiment. Now I'm going to switch on the voltage supply. But as you can see, the knob is at 0 volts. So no voltage is being supplied. As you can see, the voltmeter shows 0 volts and the ammeter also reads 0 ampere. As expected, when the potential difference across the wire is 0, the current in the wire will also be 0, since potential difference is needed for the flow of electric current. So if there's no potential difference, there will be no current. And this is our first data point, 0 volts and 0 ampere. Now let's increase the voltage to 2 volts and check the reading in the ammeter and voltmeter. As you can see, the potential difference across the wire is now 1.2 volts. And note that this ammeter is marked in milliampere. The reading in the ammeter is 30 milliamperes, which is 0.03 ampere. Note that the wire does not get the full 2 volts from the voltage supply. The potential difference across the wire is 1.2 volts. This is our second data point. Let's add it to the table of observations. Now let's increase the voltage to 4 volts. And let's check the reading again in the voltmeter and in our ammeter. Now the potential difference across the wire as measured by the voltmeter is 3.6 volts. And the current in the wire as measured by the ammeter is 100 milliamperes, which is 0.1 ampere. This is our third data point. Let's add it to the table of observations. Now let's increase the voltage to 6 volts. And we'll check the reading in the voltmeter and in the ammeter. As you can see, the potential difference across the wire is now 6 volts. And the current in the wire is 180 milliamperes, which is 0.18 ampere. This is our fourth data point. Let's fill it in our table. Now let's increase the voltage to 8 volts and check the reading in the voltmeter and in the ammeter. The potential difference across the wire is 8.4 volts as shown by the voltmeter. But this is a bit strange. How is the potential difference higher than 8 volts which the voltage supply is giving us? I think it's probably because the voltage supply is a bit faulty. It's giving us a voltage higher than 8 volts, maybe around 9 volts. That's why the potential difference across the wire is 8.4 volts. But we are interested only in the potential difference across the wire. So for our experiment, it doesn't matter. And let's check the reading in the ammeter. It shows 240 milliamperes. So the current in the wire is 0.24 ampere. This is our fifth data point. Let's put it in our table. What can we conclude from this table? That's right. As the potential difference across the wire increases, the current in the wire also increases. Let's plot a graph of this table. We will plot a current versus potential difference graph. So we'll put potential difference on the x-axis and current on the y-axis. As you can see, the graph is approximately a straight line passing through the origin. What can we conclude from this straight line graph? That's right. Since the graph is approximately a straight line, the current is directly proportional to the potential difference. And this is exactly what Ohm concluded from his experiment. He also added the condition that temperature should be constant. So Ohm's law states at a constant temperature, the current flowing through a conductor is directly proportional to the potential difference applied across the ends of the conductor. So we can write it mathematically like this. I is directly proportional to V, where I is the current and V is the potential difference. A directly proportional relation means that if the potential difference is doubled, then the current will also get doubled. If the potential difference is tripled, then the current will also get tripled. Similarly, what will happen if the potential difference is halved? That's right, the current will also get halved. So I is directly proportional to V. Now we can also reverse this relation and write it as V is directly proportional to I. That is, the potential difference across a conductor is directly proportional to the current in the conductor. Now, why can we reverse this relation? Let's take a simple example to understand. Let's say you go to a shop to buy some apples. We can say that your bill is directly proportional to the number of apples you buy. That is, if you buy more apples, obviously your bill will be more. Now, I can also reverse the relation and write it as the number of apples you buy is directly proportional to your bill. That is, if your bill is more, obviously you bought more apples. So we can reverse the relation. Now coming back to our discussion, we had current is directly proportional to the potential difference. And on reversing the relation, we get potential difference is directly proportional to the current. Now we can change the proportional relation into an equation by adding a constant. So we get V equal to R into I. This constant R is called the resistance of the conductor, that is the wire. So this is the mathematical relation of Ohm's law. But we usually remember it as V equal to IR. Now let's see how we can define the concept of resistance using Ohm's law. Let's place Ohm's law and the important formula V equal to I into R on our concept board. Let's see how we can define the concept of resistance using Ohm's law. Let's bring R to the left hand side of the equation. So we get R equal to V by I. So resistance of a conductor can be defined as the ratio of the potential difference applied across the ends of a conductor to the current flowing through the conductor. Now based on this formula, the SI unit of resistance will be volt by ampere. This is called ohm and is denoted by the omega symbol as shown here. Now let's use our table of observations and find the resistance R at the different voltages. So we need to calculate the V by I ratio for each row in this table here. As you can see, the resistance value is approximately same at the different observation points. The resistance R of the wire in the black box is approximately 35 ohm. Now this is expected since the graph was approximately a straight line. So the ratio of V by I, that is the potential difference by current, will be constant. Can we also calculate the value of the resistance directly from the graph? Yes. Remember, the slope of a graph is change in y by change in x. So the slope of this graph will be I by V. But resistance is defined as V by I. So resistance R will be 1 by the slope of this graph. Now if you calculate the slope of this graph, we get the value as 0.028. So the resistance is going to be 1 by this value, which is 35 ohms. So we are getting the same value of resistance as we got from the table. Now let's understand the concept of resistance and why Ohm called this constant V by I as resistance. Why not another name like conductance? Why resistance? So let's say we have 3 different wires having different resistances, 1 ohm, 2 ohm and 5 ohm. And let's say the same potential difference, 10 volt, is applied across each wire. Now let's calculate the current in each wire using Ohm's law. Ohm's law formula is V equal to I into R. If we bring current on the left hand side of the equation, we get I equal to V divided by R. Let's substitute the values, and the current in the three wires is going to be 10 ampere, 5 ampere and 2 ampere. Which wire has the lowest current? That's right, the one with the maximum resistance, 5 ohms. Higher the resistance, lower will be the current in the conductor. It resists, opposes the flow of current in the conductor. And that's why the constant is called resistance. But doesn't this seem strange? Why would any conductor want to oppose the flow of current in it? Why does a conductor or a wire have a resistance? To understand, we'll need to take a look deeper into the wire. Wires are usually made of metals such as copper or aluminium. Let's say our wire is made of copper. So the wire contains billions and billions of copper atoms inside it. The outermost electrons in each copper atom are loosely bound to the nucleus. These outermost or valence electrons, they leave their atom and they are free to move around in the wire. That's why they are called free electrons. Now, since the copper atoms lose their free electrons, they become copper ions. So the wire contains two things: a very large number of free electrons and copper ions. Now, when voltage, or what we call as potential difference, is applied across the wire, these free electrons move in a specific direction. And this flow of electrons in a certain direction is called electric current. The wire has a huge number of free electrons. That's why it's a good conductor of electricity. So the flow of electrons in a certain direction is electric current. But what is the cause of resistance in the wire? Remember, the wire is not hollow. It is solid and it contains a huge number of copper ions. Now, when the free electrons are flowing through the wire, they will hit or they will collide against the copper ions. So the copper ions are resisting the flow of electrons. That's why the cause of resistance is the material of the wire. So any substance, any material will oppose the flow of current through it. Copper is a good conductor of electricity, so the resistance is low. Now, if we change the material of the wire, the resistance will also change. The resistance of a conductor depends on various factors such as nature of material, length, thickness, and temperature of the conductor. But we'll discuss these factors in a separate video. Just like we have resistance of a conductor, there is another term called conductance. Conductance is the reciprocal of resistance. So conductance is 1 by the resistance. And remember, resistance is potential difference divided by electric current. So conductance will be electric current divided by potential difference. Usually the symbol G is used for conductance. So we have G equal to I by V. Now what will be the SI unit of conductance? It's going to be 1 by ohm, and this is called Siemens, and the symbol is S. Based on the concept of electrical resistance, all the substances can be divided into 3 categories: good conductors, resistors, and insulators. Good conductors have very low resistance. They allow electric current to flow through easily. Those substances which have comparatively higher resistance are called resistors. And those substances which have a very high resistance are called bad conductors or insulators. Here are some substances. Can you identify which ones are good conductors? That's right. Silver and copper are good conductors of electricity. Usually, most metals are good conductors of electricity. They have very low resistance values. Did you know that silver is the best conductor of electricity? We can make wires from silver, but that would be very expensive. That's why wires are usually made from copper. Which materials are bad conductors? Insulators? That's right. Rubber and plastic are insulators. They have a very high resistance, and so they are bad conductors of electricity. That's why electrical switches are made of plastic, and we should wear rubber slippers or shoes when working with electrical equipment so that we don't get a bad shock. Because insulators don't allow current to pass through them easily. And we are left with nichrome material, which is a resistor. Nichrome is an alloy of nickel, chromium, manganese and iron. Nichrome alloy has a higher resistance compared to conductors. Nichrome is used to make heating elements of appliances such as toasters, heaters and geysers. Due to the high resistance, the nichrome coil gets heated up and provides the heat energy needed for these appliances. An interesting question is, do all conductors follow Ohm's law? That is, the current in the conductor, is it always directly proportional to the potential difference across the conductor? The answer is no. The current need not be directly proportional to the potential difference. So the current potential difference graph need not be a straight line. Some conductors can have a curved graph. Those materials that follow Ohm's law are called as ohmic conductors. For ohmic conductors, the current in the conductor is directly proportional to the potential difference across the conductor. And the current potential difference graph is a straight line. Now, what are some examples of ohmic conductors? Examples are the wires. So these follow Ohm's law. And those materials that do not follow Ohm's law, they are known as non-ohmic conductors. Examples of non-ohmic conductors are semiconductors like diodes and transistors. Now let's look at an example how to apply Ohm's law. Let's say this bulb has a resistance of 100 ohms and it is connected to a 220 volt supply. Now how do we find the current drawn by the bulb? First, let's write down the data using the symbols. So we have potential difference V equal to 220 volt and R, the resistance, is 100 ohms. Now we need to find the current I in the bulb. So let's use the formula from Ohm's law, V equal to IR. And bringing I to the left hand side, we get current I is equal to V by R. Now if you substitute the values, you're going to get the current as 2.2 ampere. So the current in this bulb is going to be 2.2 ampere. Friends, I hope Ohm's law is super clear to you now, and you will have no resistance to this topic. To revise the concepts, just go to my website manojacademy.com and try the quiz and the top 3 questions for this video. To make it easy, I'll put the links below. So just click on the links and try the quiz and write your answers for the top 3 questions. And I promise to reply to your answers as soon as possible. And do remember to like, comment and share this video and subscribe to my YouTube channel. And don't forget to hit the bell icon to get notified about new videos. And you can check my Facebook page and do check out my website manojacademy.com for more videos like these and for the quiz and the top 3 questions on this video. I'll put the links in the description below. Thanks for watching.